Welcome back, everyone. So this is about mathematical models that describe the microscopic system. So the idealizations that I talked about at the end of section 2.1, just to repeat them, the first one is that I would like to work with an infinite sample. And while at first sight, this, you could think, this is a big complication. Using an infinite sample size allows us to use the discrete Fourier transform. If the sample were finite, you did not have periodicity, and then you would have a much messier description. But here you can really use this as a simplification. The next thing that we neglected was disorder. So this is covered in a mini course by Christian Sadel. And lastly, I'm going to neglect electron-electron interactions. And this is something that Sven Bachmann will address in his mini course. The first thing that we should describe is the unperturbed system. So what do I mean with unperturbed system? I just mean that the applied electric field and the applied magnetic field are zero. And then, okay, if we're in a single particle picture on RD, then the operator, first of all, the Hilbert space, is initially just L2 over RD. And of course, you can add spin degrees of freedoms. I shall not do so for the sake of simplicity, but in principle, this can be done. So this leads to a more sophisticated version of what I'm going to talk about today, but it's not necessary to when I really want to talk about the basics. So the other central thing here is that the potential is periodic. So I have a notion of a crystal lattice. And this denoted with gamma, and gamma is isomorphic to ZD. So it does not have to be ZD in the sense that the basis vectors of the lattice don't have to be just the canonical basis vectors of RD. They can be different. They need not be orthogonal to one another, but still, mathematically speaking, I have a lattice. So gamma is a group, and in terms of a group, it is isomorphic to ZD. And that means that the potential due to the nuclei and other electrons is gamma periodic. That is, V of x, V periodic of x plus gamma is equal to V of x for all gamma and gamma and almost all x in RD. So the almost all is, as usual, due to the fact that V need not be continuous. So it's you have to work with spaces like L infinity where functions are only determined up to what they do on a set of measure 0. Of course, in the following, I will not stress the gamma. Instead of saying gamma periodic, I will just say periodic, and it is understood that I mean this condition here. And then another way to write this down, by the way, is that you're using translation operators, which I will write as T gamma applied to V. All right, so now what we can do is we can have a look at the unperturbed operator. And I will call this the, no surprise there, the periodic operator. So this is minus h bar squared divided by 2m Laplace plus v periodic. And to just simplify my life, I will choose units. So this here is after a choice of units, I will just make this prefactor here equal to the identity. And it's just because I'm too lazy to write it down every single time. And certainly it does not really change the story in any significant way. I'm just using different units. And then under very mild conditions on the potential, so for example, you could assume that V gamma, V periodic is in L infinity. The periodic operator is self-adjoint. So importantly, and this was something that I anticipated beforehand already, and that is that the periodic potential need not be regular. So Cn regular or something like that. So basically, this just ensures that the operator that we're dealing with is well defined. So for example, if the periodic potential is in L infinity, then the domain of the periodic operator is just the second Sobolev space. So that's fairly standard, nothing to write home about. But so far, we have not exploited the fact that the potential and the operator indeed is periodic. And this is done next. And this is, let's say, subsumed under the name the energy band picture. And the purpose of, let's say, the next few thoughts is to explain this picture here, which is really central to everything else we will be doing later on. So let me begin by just noting that H periodic is, as the name suggests, a periodic operator. That is, if we remember the definition of the lattice translations on the previous slide, so these were the lattice translations here, T gamma. So this is just a shift by a lattice vector. Then the operator is periodic in the sense that it commutes with all lattice translations. And that means we can use the discrete Fourier transform or a variant of the discrete Fourier transform, the so-called Sachs transform. Or Bloch-Floquet Sachs transform. I mean, this has many names, but if you are coming from the mathematics side, it is essentially just a discrete Fourier transform. Then you can just define it as, so of course, initially you need to define this on suitable functions like Schwartz functions to make sense of the following sum. So you have to multiply the shifted function by a phase factor. And here I think it is important to also add that the function on the left depends on k and y. So here k is crystal momentum or Bloch momentum, and essentially K is an element of the torus, the d-dimensional torus, but to distinguish it from the real space torus, I will add a star here. And y is the position variable and also y is, you can think of it as being an element in a d-dimensional torus. But importantly, from a physical perspective, this torus and this torus are distinct. And there are also other identifications to make. Sometimes it is better to think of it as an unwrapped torus. So this would be a unit cell, the so-called Wigner-Seitz cell, or the Brillouin zone. And also there's one thing I'm just sweeping under the rug, and that is that this function here is quasi-periodic in K. So it's not really correct to think of this as being an element of the torus, but later on for things like band functions, this is completely enough because the quasi-periodicity implies the periodicity of these energy bands in K. So just for simplicity, picture K as an element of a torus and Y as an element of the torus, even though if you really go into the nitty-gritty details, this is not 100% correct. The point is that, so a physicist would say this operator, which is evidently unitary, facilitates a change of representation. And this means that you can, because the operator is periodic, it admits a fiber decomposition with respect to the discrete Fourier transform, with respect to the Bloch-Floquet or Bloch-Floquet-Sachs transform. So that means that if you conjugate the operator, the periodic operator, with F gamma, then you can see this as a direct integral in K of H periodic of K and H periodic of K is not just some, let's say, abstract nonsense operator. I can write it down very, very explicitly. Is just minus I gradient Y plus K squared plus V periodic in Y. And this operator acts on L2 over TD. So this is, let me just decorate this a little bit. This torus here is the torus in Y. So this operator here depends parametrically on crystal momentum K, and it acts on a Hilbert space in the variable Y. To be more precise, if you use the Bloch-Floquet-Sachs transform like I did here, then this acts on periodic functions. So you have to impose periodic boundary conditions and use the H2 regular functions on the torus. But okay, the thing is that then this operator, you know certain facts. Of course, the H periodic of K inherits the self-adjointness. Furthermore, its spectrum is purely discrete. So it consists of eigenvalues of finite multiplicity accumulating at infinity. Of course, this implies that the essential spectrum is zero. And importantly, because the spectrum is purely discrete, this gives rise to the so-called Bloch functions. So the Bloch functions are just the eigenfunctions enumerated by magnitude. So what you do here is, for fixed K, you solve the eigenvalue equation. The Bloch functions phi n of k give you a complete orthonormal basis. This follows from the self-adjointness of H periodic of k combined with the purely discrete nature of the spectrum. And the eigenvalues, En of k, if you vary k, these give rise to the energy band functions. So in fact, this is almost enough to understand this picture here. So E1, if I order by magnitude, I would have to call this here E1. This is, of course, a one-dimensional sketch. I cannot draw higher dimensional band pictures. You either have to use a computer or you have to use cuts anyway. But this is just a one-dimensional sketch. And you see that once you do this, you obtain a bunch of band functions, E1, E2, E3, E4, and E5. And the last important fact is that you can see very, very easily that H periodic is analytic in K. I mean, this is extremely simple because the H periodic of K is a quadratic polynomial in K. And if you look at the terms, the worst term in terms of the domain of the operator H periodic of K is just the Laplacian in Y. And then you have K dot gradient. This is a linear term which is infinitesimally small compared with the Laplacian. And then you have a K squared term which is also infinitesimally small compared with the Laplacian. So this function here is periodic in K, which implies, importantly, that both the Bloch functions and the energy band functions are also locally analytic away from band crossings. Of course, for the eigenfunction, that necessitates a specific choice of phase. So at each k, in principle, you have a choice to choose a global phase. And if you choose badly, if you choose unwisely, then of course you can destroy even continuity very, very easily. But the fact is that you can, if you wanted to, choose a phase prescription for the eigenfunctions so that they are locally analytic away from band crossings. And to treat band crossings, well, just what is the issue here? You can see, okay, in one dimension, you can analytically continue. But this is not true in higher dimension. So in, let's say, 2 dimensions, you would have a conical crossing, and there you know that the gradient does not have a good limit. as you approach the intersection point, and so it is impossible to choose an analytic continuation. But nevertheless, away from band crossings, so points like here, here, or here, it is completely fine to expand band functions and the like in, let's say, k minus k naught, where k naught is a point that is not a band crossing. Of course, the neighborhoods might be quite small where this expansion converges, but you know, there exists a neighborhood. Another thing that to go back, so this should explain what this picture here is. So this here is just the spectrum of the periodic operator as it depends on k. And what we are interested in is semiclassics. And to simplify the setting a little bit, what we will assume is that the characteristic energy, the Fermi energy, only intersects a single band. This is not necessary, but this simplifies some of the explanations later on. Nevertheless, let me also explain something else. So, of course, you can move the Fermi energy to different levels, and depending on where you are, the band that it intersects with is different. And this will be important in our semi-classical description because depending on which band the Fermi, or which bands, plural, the Fermi energy intersects with, I will have a different effective description. And that is because only states near the Fermi energy are mobile. They contribute to the conductance. And hence, it is not, let's say, surprising that if you pick, for example, this Fermi level here, that the relevant energy band function that will enter the semi-classical approximation is E3. And furthermore, you can ask, okay, what is the distinction between a metal and an insulator? Well, the distinction is relatively simple. If EF intersects with an energy band, well, it also means there are states near the Fermi energy. But what I can do is I can just pretend that I have a second material where the band E3 is simply absent. Then the Fermi energy lies in a spectral gap, so there's nothing in here. And hence, in this particular situation, the material, the medium, will be an insulator. So this is an insulator. This is a metal. So this gives you a description of the unperturbed system. Let's go to the perturbed system. And what that means is that I'm adding back the external fields. So here I'm adding the electric field E and the magnetic field B, which is minus the gradient of phi, and the exterior derivative of the vector potential A. And now what I can do is I can, and these are necessary, so E necessary to drive a current. So the operator that we get is quite similar to the one we had before. Let me call this H epsilon. Because I'm adding a magnetic field, I have to replace the Laplacian, which is just minus I gradient squared, by the minimally substituted operator here. And I have to add the epsilon because on the scale of the periodic potential, the external potentials vary slowly. So this was the picture that I had before. I have to add the periodic potential. And then I have to add the electrostatic potential, which again varies slowly. So let me dissect this again and be a little bit careful. So I'm having the potentials here. They are due to the external fields. And then I have the semi-classical parameter epsilon. And the presence of this parameter epsilon is just due to the fact that the external fields are assumed to vary slowly on the scale of the crystal lattice. There's also one other important factor that is absolutely crucial, namely the presence of the external fields. They break the periodicity. That means now it's no longer true that this perturbed operator no longer has a Bloch-Floquet decomposition. So it no longer has a direct integral decomposition. And this is really important because this means that the operator has much more complicated behavior. It has much more complicated spectrum, potentially. And it is not immediately obvious how we should proceed. But nevertheless, if we just place mild conditions on the external fields and on the periodic, I will be more specific later on. under mild conditions, this perturbed operator is still self-adjoint. For example, typically on the second magnetic Sobolev space. And if you pick a suitable core, so one common choice are just the smooth functions with compact support, that this operator, this restricted operator, is essentially self-adjoint. So there exists a unique self-adjoint extension. But there's also one thing that we will have to address a little bit later. And the claim is already in the title, so to speak. I'm claiming that this is a perturbation. But a big question is, okay, in what precise mathematical sense am I dealing with a perturbation here, right? That's not at all obvious. And this is, of course, not really an innocent question, because if you have if a magnetic field is present, then this operator, the quote-unquote perturbed operator, will be acting on a different domain than the unperturbed operator. So a comparison is not really immediate. And okay, as usual, if you want to know the answer, then stay tuned.